right. So, these are the few successful story of AI basically. So, you can get lot of basically motivational videos basically which tells the successful story of AI, machine learning, deep learning, right, in various domains like in computer vision, natural language processing. Voice is clear, right? Okay. So, you can see that where we use right now. So, what is the current state of art, by the way? And I think nowadays everyone knows current state of art, right, in terms of conversational AI models, or you can say large language models. So, I will share this slide. So, you can maybe I will put on the WhatsApp. So, you just go and in the I think we have a 2.5 hour break today. Right. So, you can just go through with these one, right. Then you can ask any question, right. So, you can pose many questions, many things might come in your mind. So, if you have any question from the previous session, from study session, you can ask, maybe we can discuss. I think we can move, right. Okay. These are the various sources of data from where we generally generate the data, so, right. So, you can say multimedia platforms, social media platforms basically. They can have data in the form of text, in the form of multimedia. Multimedia in the sense you can say text, audio, video, right, images, etc. You can get data from sensors, maybe some scientific laboratories, satellites, right, maybe from some literature. So, data you can get from different sources. These are the sources, right, laboratories, defense, right, and satellite, and many other places, right. So, rovers you can use for getting data from other planets. So, this is another application, the challenge. So, these are the modern problems that people are basically doing research. So, and most of the problems are basically posted on Manthan. So, government site, if you go and you see that what industry want currently, right. So, we have a Manthan, Government of India Manthan website. So, lot of industries basically post their problems there, and they invite the basically interest, you can say letter of interest, and if you bid, you can basically win the bid, and maybe you can develop product for them. So, this is one of the problem. So, that was basically in hospitals you might have seen that you have a saline bottle, right. So, in the industry it is basically the production industry that basically produce that bottle, so and fill the chemical, right. So, they use it manually. So, they have humans to inspect it. When the bottle is filled, humans are there. So, they inspect it and they just sell it packed, and machines are there, they packed it. So, there is a conveyor belt. So, in the belt the bottles are basically packed, and then some manual inspection is there. So, people are standing there, and if they see any deformation, any problem, so they just throw that particular bottle, or they put those bottles in the dustbin, and others basically went to the packaging unit. So, the challenge was that can we use the complete process automated, because there are a lot of human error. So, lot of bottles were packed, they have lot of deformation, or they might have certain particles in the in that liquid, right, that you have. So, these are the processes. You just put certain sensors, you can put temperature sensors. So, you can say that you can put image or camera, right, and then you should know certain features from that video, and you just try to come up with some model which can just tell that this is defective piece, or this is correct piece, or you can say non-deformed piece, right. Likewise, you can say you might have a data, temperature, vibration, sound, fuel. So, many times you can say if you say that we have a defense equipment, right. So, mostly you can say the trucks and other heavy vehicles. So, generally we move those vehicles to the high terrain, and every place we do not have the manufacturing unit or maintenance unit or repair unit. So, the cost of moving the basically vehicle at very far place from the repair center, and if something happened and you have to take it back to the center, it is very costly. So, can you monitor the health of the machine? So, this is a very simple and in industry 4.0 and even in higher basically versions, people try to answer these questions through AI. So, can you say that okay, your system is going to basically break after maybe 1 day, 2 days, 3 days, 1 month, 2 months, something like that. So, or continuously you are monitoring the health of the machine. So, just install certain maybe sensors, IoT sensors, receive the data, analyze the data, and just tell certain fault if it might be happening right in future. So, you have to say that this problem is basically very well known problem in AI. People say that can be diagnosed disease a priori. Can you say that if you have certain symptoms, for example, you have a high BP, high cholesterol, maybe sugar level, or can say diabetic, then so what is the probability that you might have a chance of cardiac arrest? Right? So, these type of questions we are doing in medical domain using AI, and nowadays instead of human you can replace the system with machine, right. So, you can say, can you say that can we monitor the health of a machine, health of a basically critical vehicle, critical system, maybe nuclear power plant, or some plant, maybe our petroleum plants, where the petroleum is basically somehow processed, because these are very critical places, critical industries, organizations. If you shut down the plant, right, even 1 day or 2 days, so they incur huge loss, right. Same is true for the nuclear power plant. If you shut down the nuclear power plant, it costs much, right. It takes many days to restart it. It is not very easy to shut down like computer, we put shut down and restart, right. So, can we use some AI based approach, IoT system, or even you say that okay, not exactly the IoT, because most of the critical places you cannot use internet. You can just say the local intranet or some Wi-Fi system, so that you can receive the data and do some analytics and do the prediction. And accuracy is very important here. Precision is very important. False alarm is okay, right. So, you can say false positive, right. So, you can say that is okay, but if some error is happening or some malfunctioning is there, some problem is occurring, so you have to identify it with 100% accuracy, right. So, if some problem is there, you have to identify, your model should tell, but if there is not a problem, so some false alarm might alert you, so that might not be any challenge, right. Similar is true for the medical domain, right. So, if some test says that you have certain disease, so you know that we are not relying on one test. So, you have a context behind that, that is the symptom that you might have. Then if you are diagnosed with certain disease, we follow up, basically we have a follow up other diagnosis to ascertain that whatever basically disease we have, is it true or not. For example, in case of critical diseases like cancer or some other cases, tumors. So, if some test says that you have tumor and you just go to the hospital and you get operated, it might not be a good idea. So, in order to assure that, because operation or you can say surgery is the last stage, right. If you do not be cured through medicine, so you have to go for surgery process, right. So, we have a follow up investigations, follow up diagnosis system, then we do it. So, false alarm is okay, but if the person had disease and your system says that you do not have, so disease is basically not curated on time or timely, so it can harm a human life, right. It can have a huge loss, and you know that life is you can say you cannot compare with any price, right, any cost. So, that is priceless. So, it is not saying priceless. So, priceless people might say that there is no price. It is costly that you cannot estimate the price. Okay. So, these are the real current state of art. If any student is doing project and maybe PhD student are working, so you can say even our organizations like BARC and many other organizations, they are posing their problems on different platforms. You can start working them, you can add them, right? You can help them, assist them by developing these models. And even in local industries, you can put these type of models if you develop, and you just sell to any place, right? So, health monitoring is for machine health, you can say, or you can say system health, or you can say industry health monitoring is very crucial for most of the industries nowadays, right? And everyone is adapting technology, so that's why the AI is required everywhere, right? For your training and placement, you need AI. If you want to excel yourself, you have to study AI, right? So these are the few methods. Data generation is challenge in some domain. For example, in medical domain, you might have challenge, but nowadays we are somehow overcoming that challenge by digitizing the data and ensuring certain privacy laws. So data is available in public domain for research. Then if you have a data, there might be some challenges in the data. For example, bias. Data is biased towards certain community, certain region, certain gender, right? Or certain type of noise, right? So suppose you say that you have collected data from certain faulty machine, and when you develop model, deep learning model, so this is one of the application of basically bias or you can say noise in the data. So you have a COVID X-ray image, basically image which is basically infected with the COVID-19. One image is basically with pneumonia, right? That is basically regular, or you can say usual pneumonia symptoms. And the middle one is the basically actual original basically normal X-ray. So idea is basically you have a data, you have to develop a model which classify between these among these three categories classification model. You just deploy any classification system, you will get a classification score, and by the way, very simple deep learning model CNN basically module provides around 96, more than 96-97% accuracy, high precision and high recall. But when it was deployed for the data set, real data set that are coming from some other organizations, it was failing. Accuracy was very poor. You can see these data set are available online. So the thing was that what was the reason? How can you get that? What is the reason why the model is failing? Even on testing validation data that we have in our reach, so accuracy is good. But when we deploy this model in real time, it fails. Fails means it has a poor accuracy in real time. So the idea was the data that we have used for training, so that was not following the distribution, or you can say some sense that was out of distribution, or it is very far from reality, right? Many times people in our general daily life, we say that okay, you are very far from reality, right? You don't know what is happening, right? So theory and practice both are many times different, right? In practice, what we follow, in theory, what we have, right? What beliefs we have, so that is different. Both are different. So here, when you do the investigation, so in one of the investigation for neural network models where we use computer vision or vision data, we try to basically plot the features that is extracted by every layer of the neural network. So once you plot that, you will see here, this one, the last one you can see, we have patches, right? So we have plotted the edge features from one of the layer, right, just before the dense layer, to see that what are the features that basically dense layer try to basically somehow separate, right, try to separate between these categories, or you can say among these categories. So you can find here that it is not working. So you can find here that most of the features, prominent features, you can see that are basically at the boundary of the image. The prominent features, they have a different color, you can see here. So, they are at the boundary of the image, but you know that COVIDs or any disease symptom is generally at the central position, or you can say that is not on the boundary. So, here if you see that only these features are permanent to decide whether the image is infected with COVID-19 or simple pneumonia, or you can say it is normal image. So, only age features are sufficient to diagnose it. So, this was noise. So, your model has learned the noise. So, noise was a discriminative feature, by the way. So, then it was investigated, the story is there. So, images that were collected from one of the camera X-ray machine, basically you can say, that was basically having certain dust on the film, on the basically lens. So, all the images that machine right, X-ray machine generated, so that has a particular, you know, some you know some basically points, some noise in the image, X-ray images, and model adapts it very easily. And quickly you can train it in few epochs, maybe 4 or 5 epochs, you get higher accuracy, you will stop your algorithm, right. And because we have used the data set from that only in the machine, so there was no distribution from the, you can say it was not basically well distributed in some sense. So, our model was basically biased, so biased through the noise. So, it was biased towards the noise, right. So, model has learned the only noise, right, and it says that this is a discriminative feature. So, this is challenge and debatable. Many times people say that, okay, you can say that on maybe X platform or Twitter platform, so earlier maybe 5-6 years back, you see the people were discussing about the bias in the data. Some people say this is many times you even you do not know that whether this is a bias or actually this is the feature, right. So, unless until we have a multiple diagnosis system or basically domain understanding, you cannot be or you will not be able to say that data is biased, right. So, you must have understanding. For conversational AI models, large language models nowadays like ChatGPT, whatever response ChatGPT or any modern LLMs are basically providing, you usually understand that whether it is biased or not, right. If you ask about certain religion, if it is Western religion, if it is basically Asian religion, they might give you different set of responses, right. They might be biased towards genders, right. So, if female is asking the question, if male is asking the question, some sense in the text, that query that you have written, so if some sense of basically is there about the gender, so they will respond differently. So, these are the biases that as a human we can identify very easily, but in the images or in the audios, in the basically most of the time in videos, you might not identify the bias. It is very hard to identify. Many times people say this might be the anomaly, but both are different, right. So, bias anomaly is a data that you have, so that is the correct pattern, original pattern, but bias is somehow not basically required for the model to be trained. Then in bioinformatics domain, you have a gene expression data. So, every data when we do the pre-processing, I think yesterday we discussed that you have a text data, you have to pre-process. We have to pass it through certain approaches, right. We did one approach is stemming and another one is stop word removal. So, when you do stemming, so somehow we are cutting the words, right, in order to make dictionary size smaller, right. And if the word like grammar, grammarly, you have 2 words, so both have a similar sense. So, if you remove ly from grammarly, so it becomes one word in the dictionary. Otherwise, dictionary will take another space for grammarly as well. So, that is the reason we basically try to reduce semantically somehow reduce the dictionary size by applying certain rule or word formation or grammar rules. Right. For example, go, went, gone, goes, you just convert it into go, but most of the words that we use in many forms, So, they have certain patterns, right. You can identify, you can write a regular expression for that and you can estimate, but many times it is it might incur a lot of losses. For example, if you have a word mongoose, right, if you remove es, or there are many words which uses ly at the end, right. So, it is not always that only if some word is in a certain form, it is ly is there, right. So, ly might be the content, or you can say the uh, uh, is basically you can say the main word, right, including ly. If you remove ly, so your word might not be meaningful, right. So, that is the thing in stemming. So, so here also every data, so whether it is image data, text data, or some type of basically experimental data, so they are processed through certain certain image processing techniques, certain other techniques, human intervention. So, a lot of noise will be there in the data. So, data might be noisy, data might be biased, because if it is in human control, so it depends on the human. Suppose I say that you have to label the data. So, in following slides we have that, because the data is not inherently labeled, you have to label. Some manual, some manpower is required to label the data, some experts are needed to basically label the data. For example, in X-ray image, some expert doctor you need, right, who will say that this X-ray contains COVID symptoms, this X-ray contains pneumonia, or you can say this X-ray is normal. Unless until you cannot develop the system, right, you cannot have a ground truth. If you do not know the ground truth, so any answer is correct, right, many times. And there we have certain AI approaches or some probabilistic answers, on that you can rely. So, we will discuss that those things today. So, expert is needed, and experts are human, and if that particular expert is biased towards certain thing, so whatever label the person will provide to your data, so of course that will be biased. There might be certain error as well, right. Some sentence is written, you will say that okay, if there is certain ambiguity in the sentence, someone will say positive sentiment, someone will say negative sentiment, someone will say I can't say, right. It might be neutral, right. So, if many people say that it might have positive sentiment, then you have to label it positive, right. But it might not be positive, it might inferring the negative sentiment. So, in the data pre-processing process, so there is a chance that you can have certain noise, maybe you can mislabel the sample, so expert can mislabel many times, but we rely on that. So, whatever model we are building, so we rely on the true or ground truth that we have, and we are building our model around that only. So, that is the reason we are many times we are not able to get good accuracy or a system which is basically well generalized for real time applications. So, the idea is you have a data, yesterday you have crawled the data, so you have crawled the raw data that was unstructured. Likewise, you can crawl the image data, you can download, right, you can get it from your cameras, mobile cameras, you can get video data, you can get audio data. So, these all are unstructured data. So, structured data is basically the data that you have used Pima Indian data, diabetes data, right, yesterday you have experimented. So, we read that file and directly we imported into the vectors, right, you can say array data structure, and you can plot it, you can visualize it, that data, right. But if you say that the data that you have crawled yesterday, text data, can you visualize directly? Can you represent in vector space directly? No. You have certain pre-processing techniques, you have to form the dictionary, then you have to transform your data into vectors, right, in certain vector space. And most of the popular form are basically most popular forms are basically TF, IDF, term frequency, inverse document frequency, term frequency, or binary matrix representation in text data, right. In other data, the same thing is there. Suppose you have image data and every image has a different resolution. You say that every pixel is a feature, so you can represent your data in pixels dimension, right. But if you have a different size of images, so every image has a different set of vectors, basically different length vectors. So it is not fit, it will not fit in basically vector space. Because if you say that any data point is plotted in vector space, they must have the same number of dimensions. Every data point in a vector space will have the same number of components as the number of dimension you have. They might have 0 value, but they must have certain value, right. So you have to represent your data into uniform length, or you can say fixed length basically vector, then you can plot in vector space and you can do the mathematics. So taking your unstructured data and transforming to structured data, then on structured data you can apply any machine learning algorithm. It is a very challenging process. Many times it might incur basically lossy operations in between, right. Because data pre-processing, when you say that, you might have lossy methods. For example, limitation in text data, stop word removal in text data, right. Someone says emojis yesterday, I think. So emojis will be removed or not. So if you have a tokenizer which is not capable of reading that emoji, so it will discard it. But you can basically read the emojis, put the basically synonym, or you can say corresponding text for the emoji. Instead of symbol, you just put certain text, right, which is semantically meaningful for that emoji. For example, a smiley, you just write a smile, right. So like that you can reach your text. Otherwise, text might be going to be lossy. You have basically cropped the data in some sense. And emojis are very meaningful objects present in the text, right. So they basically majorly decide the opinion, they majorly decide the sentiment, right. If you want to perform any analysis, so emojis should not be removed from the data, right. You have to handle them. Then you say that you might have a univariate, multivariate data. So if you have done statistics, you know that what is univariate. So if one feature is there, one dimension is there, you have one output vector, or you can say one input vector. Well, see, one input vector means here has one feature. Feature vector is one only. The dimension is one. For example, in time series data, most of the time the data that we receive it is univariate, right. So you can say one value is changing, only one feature, one value, one vector, one dimension is changing. So value is changing only across the one dimension, and output might be anything. So this is called univariate. Only one dimension is changing, one feature is changing, right. We call it univariate. Multivariate is basically you have multiple features, more than one features in the data. So in statistics, people gave the name univariate and multivariate. Then another one is unimodal or multimodal. So there are different theory behind this. So there are two popular theories behind this multimodal and unimodal systems. One is according to distribution, which says that unimodal means you plot the data, you have one mode only, one peak you have. Multimodal means you have multiple peaks in the data, right. But here the sense we are trying to tell you here. So unimodal and multimodal is, unimodal means the data that you have received follow the same one single distribution. It is generated from single source, right. It might contain only one form of the data, either text or audio or image or video. But when we go for multimodal data, so multimodal data is basically a mix of many things. Even if you have a text data, it might be a mix of multiple languages. It might be a mix of audio and text, right. It might be a video and text. It might be images and text, audios, right. So data is basically mixture of different form, right. It is in many form, right. So we call it multimodal. So here you can say different type of sources are basically used to basically generate the data. For example, you might need cameras, you might need certain sensors, you might need some social media sites, right, some blogs, a place where you are basically generating the data. So, multimodal is basically a mixture of many form of the data, and at the same time you can say that it might have a different sources. You have collected data from different sources, right. So, one might be the audio system, another might be the video system, then another might be the text system where you are just typing, right. So, the aim is whether you have a unstructured data, maybe one is we call it semi structured. So, we cannot leave it, maybe you have a huge data, but few of them are labeled, or few of are they are not labeled, we call it supervised and unsupervised. If your data is labeled, we call it supervised. If it is not labeled, we call it unsupervised. If it has a partial label, we call it semi supervised. The similar way here. So, we have unstructured data, we have structured data. So, you might get data which is partially structured, right. So, few things are in structured form, few things are not in structured form. For example, HTML, yesterday you might have seen the HTML source file, right. So, you have a different tags there, and between the tags you have certain component you have written, right. So, the thing that you have written in between the tags, right. So, opening and closing tags, so they are mostly text, right, in the text form. So, text is unstructured data, but you have tagged it. So, some structure is present, you know that what is the header, right, header 1, header 2, header 3, right, you have a body of the page, right, then you have a different image source and many things you have. So, it is somehow tagged data, right. Similar way you might have seen JSON files. If you are working in large databases mostly, then you might be knowing MongoDB, right, and many other large databases. So, generally we try to store the data, if you have a large data set, so we store in different format, we call it JSON format. So, JSON format is basically, you can say in some sense we have certain tag preserved there, you can say that maybe imply name, age, something. You might have a description as well, right, and different record in this JSON file might have a different schema, means different attributes, right. So, that format is used by databases like MongoDB to basically store large data set and query them fast. So, the same thing is here we call it semi structured data, because partial tagging or partial structure is present. So, we can easily transform them to a structured form, right. So, because our machine learning models, whether they are deep learning models, whether they are standard machine learning models, they need data in structured form. And yesterday you have seen that P-mind in adapt is data, you can directly apply the models and you can get the solution. But for text data you have not completed it. Suppose I say that can you provide the sentiment whatever data you have crawled yesterday, you might not have not completed it yet, right. The reason is that there are other steps to do, right. You have to transform your raw data to a structured form in vector form, then you can deploy any algorithm whatever you want. So, in today's session we will see that how we are going to perform these type of things, right. So, these are the unstructured data, semi structured and structured data, you can see here. This slide basically convey the information. So, our goal is to from unstructured or semi structured to structured form, vector space representation. So, in that process you might say that you can do certain feature extraction. If you are domain expert, you know that what feature might be the relevant for this particular task, you can extract it. Otherwise, you can just use raw data, raw features, maybe for image data you can say pixel is a feature, in text data you might say that every word is a feature, right. So, those things you can use, all right, and these are the some example we have given, right, image data and speech data, right. So, these are the few problems that we generally encounter. So, classification and regression are the traditional AI problems, or you can say machine learning problems. So, every data we say that whether we have to do regression or we have to do classification. But there are many other problems like ranking. So, given a set of images, set of photos, set of objects, can you rank them? can your AI model rank them, right? Machine translation, document summarization, image captioning, right? Maybe query, question and answering, you ask any query, you have to basically get some response, right? So, they are not exactly classification or regression. They might align with certain problems, but they are different problems. So, how will solve these problems, right? So, there are many problems. It is not limited to only classification and regression. Right? Maybe you say nowadays people try to say that can you generate the description about any sort of prediction, right? So, can you generate the description? Can you write a story? Can you do style transfer? So, style transfer means you have some handwritten document of yours. Can you develop a model which can basically learn your writing style, and it can generate the document in your writing style, right? So, style transfer, can you clone the models, right? Style transfer means the way you are speaking, you are performing the actions, can you transfer those actions to a different basically person, to a different image. So, that is why a lot of deep fake websites are there. You just put your photograph, you just copy certain styles from somewhere, right? And you can just say that you can make the different pirated, or you can say not pirated, you can generate the fake videos, fake text, fake data. So, that people should not understand that whether this is real or fake, right. So, that is the challenge nowadays. So, those are the problems in AI. So, we are dealing nowadays, right. This is the supervised learning system. So, we have already described about the supervised data. So, you have expert, you have employed basically experts to label the data. So, labeling is very costly process, data labeling, because nowadays you can say that we have a large number of social media text, and if you say that you need some expert to basically tag it or label it, it is very costly. You have to pay it, right, pay for that. So, machine learning model, if they need supervised data, so it means that any algorithm, if it is required that you need data and its response, or you can say its output as well in the algorithm, we call it supervised algorithm. What we call it? Supervised algorithm. So, supervised algorithm takes two things as input. One is the data in vector form, vector space you can say, and the other thing is the output. Output might be also a vector, so that will be a vector or a scalar you can say. So, if both the things are required during the training process, learning process, the algorithm is called supervised learning algorithm. Right. So, it means that your data must be supervised, right. But we will show you that something will show that neural network. So, neural network, one of the machine learning model that we have, you can say that we are going to discuss more in this in the session, neural network. So, neural network is inherently supervised algorithm, right. So, if you do not provide the label data, supervised data, so it will not work, because the fundamental principle behind the neural network is to minimize the loss function, and loss is computed using the ground truth, and ground truth is your label. So, loss function that you will design is basically that needs label information, that needs supervised information. So, neural network algorithm is supervised algorithm, but many times we just provide the data to the neural network to just learn itself, right. For example, large language models. So, can you imagine that can you employ a set of people who can label whole data, whole basically internet data that is available in open source and in public domain? Can you imagine anyone can do, any company, any organization? No, because you might need many millions of people to experts basically to tag it correctly. So, you have only unlabeled data with you. So, in the whole basically internet system, you can say, or you can say the data that is available in public domain, whether it is text, audios, videos, images. So, they are not labeled, but we have to develop conversational basically AI systems, for example, large language models. So, what we do? So, we deploy neural network needs that information. So, we generally write algorithm to generate labels, right. So, in order to learn the language, we follow the comprehension technique. So, you can see that during the school time, so how we try to learn the things. So, you have a basically chapter, then you have a some certain comprehension chapter, you can say, then you have to basically fill in the blanks, right. You have basically some text, some piece of text, you have to fill the values, right. So, certain places are blank, you have to fill that. This was the basically way we were basically learning the things, right, during our school time. So, the same thing is used here. We have a data, we have a whole corpus unlabeled data, just try to generate the labels from the data. So, you just what you do, you just do the masking. So, masking is basically remove one word and just say that this is the label we want to predict. So, make one place blank, you say that this fill in the blank problem we want to do as a prediction problem, inference problem. So, what should be put in that fill in the blanks, right. So, just use the algorithm, apply the algorithm to make the corpus intrinsically labeled, right, and just train your model. So, that is the philosophy behind large language models, whatever GPT we have nowadays, or Bard, Google, Gemini, you can say DeepSeek and any other model. So, what they are doing, because they do not have labeled data, so they try to learn the language itself, right. So, whatever data is available, so they try to learn by just masking few things. You just mask it and you just say that okay, you want to predict that value, and the ground truth you know that because you have masked it, you know the correct label. So, based on that you just compute the loss function and just do it. So, this is the philosophy behind large language models. So, neural network is supervised algorithm, but many times people say that okay, it works for unsupervised data. Yes, it works, but you have to provide somehow label. So, you have to design the algorithm approach which basically generates the label basically intrinsically during the learning process and compute the loss, right. So, this is supervised learning algorithm I just said here. So, one of the popular example maybe I can say in neural network is autoencoders. So, people say autoencoders are unsupervised, but actually neural network that we use in autoencoder is supervised algorithm, learning algorithm. So, that needs label. So, in that case the label is the data itself, right. So, that is used to basically encode the data, whatever feature vector we have. We might have a high dimension data, we try to reduce the dimensions, right. We try to compress it, we try to encode it. So, autoencoders are used where in output label that you want to predict, the ground truth is the same as the input, right. And the dimension or encoding layer basically decides the number of dimensions that you want to basically compress or encode, right. So, neural network is one of the architecture in machine learning. You can approximate any continuous function in certain bounded region, or you can say in certain domain. So, this is called universal approximation theorem, right. So, neural network can approximate any function, right, continuous function within certain domain, right. So, it can do if you have a loss function, good loss function, it will try to minimize the loss function, right. We will discuss in optimization. So, many theories we will discuss maybe today, right, about the optimization process and what kind of loss functions we generally optimize and what are the challenges, right. Then you just deploy your model in the real time, you just get the data, of course, you get the extract the feature, you just represent your real time data into the vector space and then get inference from the model whatever you have trained. right. This is unsupervised learning where you do not need label information, right. So, clustering is basically K-mean clustering, hierarchical clustering, and many more clustering algorithms you might have heard the name, right. We will basically discuss few algorithms today. Maybe in the practice session we will share the codes so that you can practice, right. So, supervised and unsupervised. Supervised you have already done yesterday, right, remind and average date. So, all those are supervised algorithm, you have label information there. Unsupervised you can just say the clustering algorithms you might see, and then you just have a real data, you just again transform it into the vector space, then you just say that which cluster you want to assign this given a particular real time data, real time sample. So, which cluster it belongs, basically which group it belongs. So, you assign that group to that particular sample. That is the learning in basically unsupervised sense. This whole significance test we have already discussed, that how can you do it, maybe we can discuss in more detail if anyone want. Right. So, what is the time right now? 10:50, right. Okay, so we can basically develop some basics behind this, right, in 5-10 minutes. Okay. So, see we have a data, right, you know that you have data, you can crawl the data, you have algorithms, you have machine learning models, AI models, and there are many. And now the challenge is we try many things, but the generalization accuracy is poor, right. You have data, you have trained your model, you say that your model is working perfectly fine, it is fine, you deploy it in real time, but when you deploy it in real time, it started facing a lot of challenges, accuracy is poor. So, it means that is fundamental challenge, right. So, we have to go the other part of this learning process, learning things. So, we have to theoretically guarantee certain things, right. So, we have to guarantee, we have to put certain guarantee, deterministic guarantees. Can we do that? So, one simple question is, how many samples do we need to a certain accuracy? Suppose we want to achieve 99.9% accuracy. So, in order to basically achieve that accuracy, so how many samples do we need? So, huge is an ambiguous word, right. Someone will say that huge is 10,000, someone will say no, 1 million is huge, someone will say no, 1 million is very small for me, we need many more, right. So, what might be the how can you estimate, at least can you say that at least if you give these many samples, we can guarantee this much accuracy. There are challenges. So, here in this few slides we have for that. So, where we build the learning theory. So, we will see that how learning happens, right, and what are the estimates, right. If your features are basically IID, independent and identically distributed, they follow the similar distribution, then we have guarantees, right. For a certain error, certain test error, you can say that these many samples we need, at least these many samples needed. If you have more samples, there is no issue, but if you have less number of samples, there are many issues. So, we will try to fix the guarantee about the least number, how many samples at least we need to reach a certain accuracy, certain error bound, right. So, here why the challenge is there, because the data that we have for building the model is very less, right. Even you say that we have 1 million sample, they might not be basically sufficient for training a good model. The reason is that data is basically, you can say we have you can say that if any data set that you might have, if it does not follow the real distribution, if it cannot mimic the real distribution, right. So, we generally assume Gaussian, right, but in practice it might not, right. So, if your data is follow certain distribution, right, your feature vectors follow certain distribution, and you have a data through which you can generate that distribution, mimic that distribution, you can say that data might be good for developing a good model. But in practice, we collect data samples, few samples, for example, human faces. You might say that you have your own mobile phone, another person has a different mobile phone with different resolution, right. You might have maybe you can store data, your images on cloud, you can get from some public resources, right, you can get the data, image data. But suppose you have built your model on the data set that is available on public resources, maybe on internet, you just download the image data, face data, train your model, and just click one picture from face picture from your mobile phone and just provide it to the model. Just you will see that it is not able to classify correctly. So, it means there is certain difference. It means that the real time the data that will come to your model, that will be basically fed to your model, is different, right, than the data that you have trained, you are going to train the model, right. So, that is the challenge. So, this is, by the way, in deep learning we call it distribution shift, right. In statistics we call it distributional shift, that your training and validation you have a different distribution, and real time you have different distribution. So, this distribution shift is huge, then of course, your generalization accuracy is of course going to be poor. So, generally we have a very small number of samples from this real distribution carry many infinite many samples, and we have only reached to the data that we have in our hand, right. And in that data we basically split it into validation part and test part and train part, and we say that okay, our model works fine, right, if it has a good accuracy and test data. So, the same thing we will see here, why is this happening. So, this rectangular dotted rectangle can you see here, right. So, we have a rectangle here, we have a circle here, and actual distribution we have. So, dashes are basically dash and this crosses are the data set that we have. You can see in this data there is the actual distribution, U is the actual distribution of the data. You can say the circular hypothesis, a circle here is a correct hypothesis, correct classifier. If somehow you identify this circle, right, around this positive samples, or you can say inside the negative samples, it is a correct classifier. But we do not know all these. So, what data we have? So, we have the data, this is the training data, you can say S. So, that is this dotted rectangle we have. So, this is the data we somehow we have captured, right. And now our task is to identify this hypothesis class C. Right. So, this is the challenge. So, just say if you are able to identify this is the this model C, this circular model, then you have a zero error, right, during the training, during the validation, during the testing, and also if you deploy in real time, because this is the correct hypothesis, or you can say true hypothesis that you want, right. So, in machine learning our aim is to identify this one, but we do not know. Here we are able to visualize in 2D. So, we know that circle might be the fit, but if you have high dimension data you cannot visualize. Even you try to visualize using some dimensionality reduction techniques, lossy techniques. So, because they are lossy technique you cannot actually visualize them, right, and many times they have many nonlinear complex patterns. So, you cannot visualize, you cannot understand well, right. So, we say that let us see be the concept, or you can say true function or true hypothesis which is capable of modeling the unknown data distribution D. Right. So, unknown data distribution means that complete distribution that we have from test samples. You can say unknown distribution is the test sample, or you can say real time sample. So, any sample can come in real time, right. Training sample S, that is identically independently, you can say independently identically distributed from this distribution is available to model the concept C. So, what is our aim? Our aim is to identify a hypothesis. We have to look for a hypothesis H. Correct hypothesis is circular function, right, you can say model. So, we have a hypothesis class, right, and we want to identify a model H, that is training model, the algorithms that you might have. It might be linear regression, logistic regression, Bayesian classifier, decision tree, random forest. So, H might be anything. So, you just say that if your hypothesis capital H is linear models, then H will be any linear model, right, any linear plane, you can say hyperplane. If H is a basically you can say capital H is a class of maybe nonlinear functions of certain types, maybe you can say quadratic function, cubic functions, then that is so H is a member in that class. You say that capital H is a tree based classifier, so all possible trees up to certain depth and with fixed number of branches, right, might be the member of this particular class, you can say. So, aim is to identify this one, you can say behavior operation. So, H is the model that we are training, a small h is the model that we are training. C is the correct class that might be, we do not know that. So, we want to basically reduce the error. So, we want to make our H as close as possible to C. You know this operation, if both are same, C and H both are in agreement, right. So, you just give a sample, model C also says a particular class and model H also says the same class, then is there any error? So, this JOR, right, so you have JOR operation here. So, there is no error, but if they have disagreement or they are not basically agreeing on a particular inference or prediction, so there is an error. So, our aim is to basically bound this agreement on the error, disagreement. So, we are bounding the disagreement, epsilon is basically the error in real time that we want to achieve. So, this disagreement we want to bound, it should not go beyond this, right. It maximum error that you can allow is epsilon, and we use probabilistic probability here. So, the region the error we want to range from 0 to 1, right. So, that agreement we want to ensure. So, we call it basically acceptable hypothesis. If we are able to bound the H that we have used, small h basically we are doing, C is the actual one that might be, that is unknown to us. So, our aim is to bound this one. So, this is C, right, tree 1. Let we have found H1, H1 is our model. We tried and somehow we got this one. So, you just see that you have to see, you will get certain error, right, because your training model is H1, actual is C. You can say there is a huge gap, right. So, they are not exactly coinciding each other, right. So, the error region is there. So, agreement region is there and error region is there. So, we have error. maybe say that another model is there H2, because you do not know C, right, C is unknown to you. We are trying to reach to the capability of C, right, or you can say we want to identify C, but we are assuming it might be something like this, right. So, just see H2, you have a different error. So, likewise our aim is to identify, so you just try many models, you just identify the good hypothesis H, which basically try to bound this error, right, and this we want with certain confidence delta. So, delta is the confidence. So, this must happen with certain probability, because 100% guarantee you cannot give. We said that okay, whatever statement we are saying that this hypothesis, any hypothesis Hi, right, is in disagreement with concept class C, or you can say true class C, true basically hypothesis C, under certain error is bounded by certain confidence, you can say with this probability, with 99% probability, right. With 99% probability, so delta is the inverse of that confidence, we call it basically that should be bounded. So, this error must be bounded, so must be upper bounded by delta, it should not be greater than that, it should be less than the inverse of the confidence, you can say. So, it means that if you say that okay, we want greater than delta with high probability, right, 1 minus delta. So, if you just say that you just put minus where, so here you just write 1 minus delta. So, this inequality will reverse, right. So, that you can say that we want basically guarantee that error should be bounded, real time error should be bounded, it should not be greater than certain epsilon here, and this inequality is true with certain confidence, certain probability, we call it delta, right. So, if you find a hypothesis H1 which perfectly aligns with the true hypothesis, true concept class, then of course you know that what will happen, error will be 0, right. This is the perfect model we want, and this hypothesis is called consistent hypothesis. What we call it? Consistent hypothesis. So, if you have found the true concept class, right, so we have consistent hypothesis. So, it has a similar capability as your true basically model, or you can say true concept class C has, right. So, you just see this inequality, the first one. So, we want guarantee that H and this C are in disagreement with this error epsilon. So, they should not go, the error should not go beyond epsilon, and this is true with, right, at least this guarantee, this with this confidence. So, 1 minus delta says the confidence, right. So, delta is 0.1, so it means that we want 1 minus 0.1 is 0.9, right. So, we want this with 90, at least 90% probability, with at least 90% confidence, we are able to say that the hypothesis class H has maximum error bounded by this epsilon. Okay. Both are same here. So, the right hand side is the just inequality is inverse, right. You say that the agreement is greater than that, the accuracy is greater than the error that you have, right. So, accuracy we need more with this confidence less than delta, right. So, you can say. So, both are basically just mathematical representation. So, just the first one, so you will get this one in many books, right. What it says that C and H, they are in agreement, right, and this agreement must not basically exceed this epsilon, and this is true with at least 1 minus delta probability, or you can say confidence, and this is called probably approximate, or you can say approximately correct learning. So, using this you can say we are not going to basically discuss more math here. So, giving you the idea. So, let another hypothesis is H2. So, H1 you know that it has the same capability as C has on the data that you might have. So, here you have H2 here. So, can you see what is happening here? So, the C was basically the concept class C is enclosing all the positive samples. So, concept class S2 also encloses all the positive sample inside it. So, it will give basically the samples which are basically inside this C, and you will see that for all the samples for which C is giving the correct result, this S2 is also giving similar, but it has a certain error, right. But so for the C class, you can say the C model, or you can say the model hypothesis C, it is in agreement with the samples for which C is giving the correct result. So, C and H2 are in agreement. So, this is consistent hypothesis. Even H2 is not a good model, right. So, likewise you can say here, because you have the training data in your reach. So, H2 and H1 we are assessing through only the training data, we do not know the true distribution, we have only S is basically sample distribution, sample data that we have, right. So, the gap between the training error, you can say this error is basically on the training data. So, whatever training data you have, error as and the epsilon, we know that this is the basically real time error, we are generalization error we are going to basically obtain, or you can say we can get in real time. So, this is the inequality. So, how the real time error is bounded? So, real time error is basically upper bounded by training error plus this epsilon that we found from the PAC, right, PAC, probably approximately correct learning. So, without wasting your time, so we are just moving and just telling you the inequality here. So, M is the number of samples here. If your hypothesis class is basically consistent, so on training data you have 0 error, right. You have a model, training error is 0, it means you have 100% accuracy, right. Then this inequality holds, M is greater than 1 by epsilon log of H, right. H here, H, capital H, you know that what is capital H, it is the hypothesis class. So, hypothesis class size might be finite, might be infinite. So, number of members that you might have in that class, suppose I say that you have a linear model in 2 dimension. So, linear model in 2 dimension you might have infinite many linear models, right, with different intercept, with different slopes, you might have a many many lines, infinite many lines. So, hypothesis class you might not you can say might not be countable, it might be infinite. But if you say that if hypothesis class you can count it, it is countable, we will show you certain examples where you can say hypothesis class can be countable. If you can count it, if you can compute mod H, then this inequality holds. So, for consistent hypothesis class H, the number of sample at least you need that you need for the for getting this epsilon, at the most epsilon error is linearly dependent or directly proportional to the size of the hypothesis class, and it is inversely proportional to the delta. So, it means that you can say it is directly proportional to the confidence. So, 1 minus delta is the confidence, right, delta is the parameter. You can say with at least this probability, the true error this one. So, true error is basically the distributional error, you can say the real time error is bounded by this one, right. So, if you want to reduce true error, number of samples you need more, Can you see the equation? So, it is inversely proportional, and this is for consistent hypothesis. If your training error is 0, this bound will hold. So, it means number of samples, if you increase the number of samples, the error, true error is going to be reduced, right. And of course, with certain confidence delta is a parameter 1 minus delta confidence. But if error is not 0 and hypothesis class is bound, you can compute mod h. So, then this is the inequality, right. So, this number of sample is basically bounded by the inverse of the quadratic error, you can say square of the error. So, if epsilon is 0.1, so 1 by epsilon square will be 1 by epsilon will be 10, right, if epsilon equal to 0.1. So, 1 by epsilon is 10, 1 by epsilon square is 100. So, if in the previous case you can see if epsilon is 0.1, we want 10% error rate, and you just assume everything is constant. So, at least 10 samples you need, right, or multiplier of 10. But in the next one, if error is not 0, error on training data is not 0, you need at least 100 times, right, this constant whatever you might have. So, multiplier is 100 now, quadratic. So, if you want to achieve an epsilon error 0.01, so 0.01 means 1% error. So, what will the multiplier factor here? 10,000, right. So, 10,000 times this log of mod h plus ln of 1 by delta. Right. So, roughly you can say that you need more samples. If your training error of the model is not 0, so you need more error. So, you can say error is bounded by this one, the last one you can see. So, again you need more number of samples. So, in consistent hypothesis you are not, you can say that if you compare with the agnostic learning, or you can say this where error is not 0. So, we need more number of samples here when comparing with where error is 0, training error is 0, right. Then another challenge is if this hypothesis space that you have mod h, you cannot compute, it is infinite, then what will you do? In order to establish the theoretical basically bounds on the number of samples, we compute VC dimension. VC dimension you might have heard the name Wapnick, right, Chervonenkes dimension. So, this is used to basically somehow approximate the model complexity, how complex the model is. So, if you are not able to compute mod h, you can compute VC dimension, and then you can see here. So, the equalities basically inequalities are here. So, similar to the mod h, you can say it is basically directly proportional to the number of samples, right. If VC dimension is high, so in order to get certain bound on the error, you need more number of samples, right, to train, otherwise your model will going to overfit. So, the data set if you have, it has large number of features, less number of samples, very simple model is going to overfit. So, we will discuss this concept, what is overfitting and underfitting, maybe in today's session. Maybe we can stop here, and I think for 5 minutes, and we can then continue, right. We do not have any break, right? Do we have any? Okay, I think we have a break at 12, right? Okay, so we will have a break at 12, then after 2-3 minutes we will do it. I think it is going a little heavy today, right? I don't worry, we'll do something funny maybe, because now we have started a little math, right. So don't try to remember it. So you will get all the derivations, right, if you want. Only the thing is that I am just making this, giving you the sense that how many samples do you need. So from where the concept that we need deep learning models or AI models need large number of samples, right. So there is a challenge also. We have shown that you do not have a complete distribution. So, training sample is just you have sampled. Even you say that you have millions or trillions of samples, so they might not be representative of the distribution. So, we are continuing here. So, here also you can see that the number of samples at least that we need is directly proportional to the VC dimension, right. So, VC dimension is another, you can say the measure of the model complexity, you can say in some sense hypothesis class complexity. So, like if it is countable, then previous bounds can work, but if it is not countable, then VC dimension is computed. If you are able to compute VC dimension, then you can just get theoretical bound here. So, of course, it is inversely proportional to the epsilon, right. Similarly, and true error is basically bounded by the training error plus this epsilon, right. So, this quantity is epsilon, right. So, this quantity is epsilon, right. The second term, okay. So, just see here, actually error, the first term, that is error on the training data, S is a training data. It is model dependent, right. So, you might have logistic regression, you might have a maybe superconductor machine, you might have other models. So, error on training data you will get, because H is your model, you can deploy that model, you can you can perform inference on training data with your model. So, you will get that error, plus the true error is dependent on other things, and these things are like number of samples, how many number of samples do you have. What is the VC dimension of hypothesis class capital H, from where this h small h is a member, and of course, the delta parameter. So, it defines the 1 minus delta as a confidence, you can say. So, it depends on these things. So, you can see here the second term, the first term whatever h you have chosen, so you can directly get. The second term is basically the structure. So, what structure you have chosen, from where you have chosen this h, right. What confidence we want, with what confidence we want to bound this error, what is the basically model complexity or you can say VC dimension of the hypothesis class. The same is true for others, right. So, you can say the same thing. You have two terms, right. First term is in your reach, second term is basically the information that you, number of samples of course you have, right. So, we try to increase during basically using augmentation techniques if possible, otherwise you do not have anything to do. Mod h, or you can say the number of possible members in this hypothesis class, with the structural property, you can say structure of that hypothesis class, how can you count it, then delta parameter. So, you can say one is the basically empirical risk, we call it empirical error. So, empirical that you can obtain through experimentation. So, h you have chosen, you just on your data, training data, you just compute the error, but the second part is due to the hypothesis class that you have chosen. So, if your hypothesis class is not correct, it is not good, it is not aligned with the you can say true concept class, then of course, this error, the second part will be there always, some value will be there, right. So, that is the reason we try to include as many S sample we can, right. So, in order to reduce the true error, basically real time error, our aim is to pump as much data as we can. So, that is why we say that machine learning models are data hungry, but we have bounds on that, at least these many samples we need to perform certain guarantee. So, here VC dimension. So, VC dimension is a very popular approach to compute the model complexities. So, most of the machine learning algorithm that we have, so we can compute the VC dimension of those models. Then you can say that how many samples at least we need to get to a certain guarantees for the model, right, in real time. So, anyone knows VC dimension? Okay, so maybe we can use a board. I think we don't have any board here. Okay, we'll do in the tutorial session, don't worry. So VC dimension says that let you have a binary class classifier just, right. So idea is you just say that it basically says that how many samples, how many maximum number of samples a particular model, right. So particular model can correctly classify for all possible labelings. So that number of samples, right, that maximum number of samples, right, defines the VC dimension of that hypothesis class. So what it says that, maybe I am just making you understand in a simple way. You have a hypothesis class, you say that let you have logistic regression, or you say that you have superproductive machine as a classifier, and let you have a 2D data, 2 dimensional, 2 features are there in the data. Let I say that you have 5 samples. So if you have 5 samples and it is a binary class data, so how many labels you can provide, how many possible labels you can provide to the data, how many possible labelings you can do. 5 samples you have, every sample can be labeled as either class 1 or class 2, second sample class 1 or class 2, third sample class 1 or class 2. So how many possible labelings you can do for 5 samples? 5 C 2. So this is not, we are not choosing 2 samples out of 5 samples. We are saying that how many possible label data you can generate. So every sample can have 2 labels, and you need labeled data. So every sample should be labeled. So you have 2 into 2 into 2 into 2, 5 times, right. So 2 power 5. So these many possible labelings will be there. So if you choose any hypothesis class, and any member in that hypothesis class, if capable of classifying, correctly classifying with 0 error, right, correctly classifying all the samples for all of its possible labelings, then you can say that that particular hypothesis class cites these 5 samples. So maximum number of samples that a hypothesis class can cite. Cite means for all of its possible labelings, it can correctly classify without any error, right. That defines the VC dimension, right, of that hypothesis class. So for example, if you see you have a linear models, all right, let you have a linear model, line is a model. So how many sample it can correctly classify? So you can say let, you can start with, so how this VC dimension is computed. Generally the layman approach is that you start with 1 sample, 2 sample, then 3 sample, 4 sample. So when you see that the hypothesis class is not able to classify, you stop there, you just see that which, what was the maximum number of sample that it was able to settle. You just say that this is the VC dimension. So for example, here for linear models, you can say for this line, let you have 3 samples. So you might say that 2 samples, you have a line as a hypothesis class. So if you have 1 sample or 2 sample, let you have 2 sample, you start with 2 sample. So you just put any possible labeling. So if you have 2 sample, how many labels you can provide, how many possible data sets you can generate, right, you can say 4. So you can say class 1, class 2, class 2, class 1, class 1, class 1, class 2, class 2, right. So you can say that there exists a line which can identify, which can classify, which can get a boundary between these class 1 and class 2, linear boundary, right. So we are trying with 3 samples, you can see here. So you have all negatives, you have a 2 positive, 1 negative, right. So you have 8 possibilities here. Can you see here? So there exists a line which can basically correctly classify or correctly discriminate 3 samples for all of its possible labelings. So these are only the possible data sets you can generate for binary class, right, for 3 samples. Now go to 4 sample. So just take 2 cases, I am just giving you, where you can say the corner places you have a class 1 label, and the off diagonal other corner you have a class 2 label. So you will see that. Can you draw, everyone please? Just draw a square, or you can say you just draw 4 samples you just draw. So just put 4 dots, and the off diagonal dots, you can say diagonal dots, you just, so one diagonal you just put one label, another diagonal you just put another label. Class 1, class 2, just draw it, just, right. And just can you tell me that is there exist any line, can you have any line which can basically do the classification for this particular thing, arrangement? Because this might be one of the sample that you might generate in this out of 16 possible labelings, right. So you cannot have linear classifier, so none of the line can do that, right, classify correctly. So these are the 2 cases you will see, all other cases you will do correctly. Out of 16, these are the 2 cases where you can see that your line is not able to saturate, it fails for 4 samples, but it is capable of scattering 3 samples. So the VC dimension of line is 3. So instead of line, now take the plane, just increase one dimension and line becomes plane, right, linear plane. Then you can see that if you have a linear plane, whatever data you have, you just try to visualize it. You just say that the diagonals are basically somehow aligned such that you can have a plane, you can discriminate it, right. So you have 4 samples, so plane is going to basically correctly classify. But if now you take 5 samples, so there exist many basically possible labeling for which linear plane that you have in 3 dimensions is not able to correctly classify. So that is why the proof says that linear models in D dimension have a BC dimension of D plus 1, right. So here line, what is the dimension of line? It has 2 dimensions, right, x and y coordinate you have 2 dimensions only, right. So VC dimension for line is 3, VC dimension for basically linear plane is in 3 dimension, it is 3 plus 1 4. For linear hyperplane in D dimension, it is D plus 1. You can easily prove it. Okay. So that basically is that is used here, VCH. So given a hypothesis class, you know that mod is infinite, there are infinite many members. You can say line, infinite many lines you can draw in 2D. So hypothesis class you cannot count, right, because it is infinite. So we can compute VC dimension, right. So these are the 2 methods. If you one of the popular method people use VC dimension to assess the model complexity, right. So the error is bounded by this one. So some order of this VC dimension. So it means that if VC dimension is high, the true error is going to be high, and VC dimension is directly proportional to the number of features for linear models, right. So line is a linear model, plane in 3D, linear plane, right, is a linear hyperplane in higher dimension, right. So that is basically you can see bounded by this. So if BC dimension is high, then error is going to be high, because this is somehow directly proportional to the error, right, true error. So our task is to reduce the VC dimension. So if your model is complex, non-linear, then VC dimension is even very high, very large, right, because linear models can be, non-linear models can be approximated by linear models, right. You can approximate different, right, many combination of linear models you can used to approximate any nonlinear model. So, you can say if you have a nonlinear model, then VC dimension is even very high. For Gaussians, or you can say radius basis function or kernel, if you have studied subproductive machine, there are many basically models, nonlinear models, where the VC dimension is infinite. Then there is challenge. So, this inequality will not work then, right, because VC dimension is very huge, right. So, how can you compute the bound? But in itself, if VC dimension is high, so true error or real time error is going to be high. So, what you can do? If VC dimension is high, what you can do? How can you reduce this second term? You know that VC dimension is a structural basically computation. So, if your structure is fixed, hypothesis class fixed, VC dimension is fixed, it will not vary, right. Now, what you can vary? You can vary m is the number of sample. So, you just try to increase the samples, you try to augment the data. If you see overfitting, so some true error is very high, where training error is less, true error is very high, which can say real time error is very high, test error is very high, training error is very small. So, what does it mean? It means that this quantity is huge, right, second term is very huge. It means that you have to take care of the second term, try to reduce this component, right. So, how will you reduce? By increasing the number of samples or reducing the confidence. So, 1 minus delta you just reduce, say that okay, with 60% probability we want this answer with this quantity, this component will be reduced. But for high confidence, if your delta is fixed, VC dimension, because you have chosen hypothesis class, so VC dimension of that hypothesis class is fixed. Suppose you say that you want to fit a linear model in D dimension, so VC dimension is D plus 1, it is fixed. Only the thing you can change here is you can vary is number of samples, right. So, that is the reason we augment the data. If you have less number of samples, we augment it, right. And another one is, in order to achieve basically this real distribution D, right, you try to augment somehow. You just put certain noise, certain thing, so that you can try to mimic the actual true distribution. So, one thing I want to tell you here, this is the only reason attacks are possible on ML models, because the sample that on which we trained our model, this H, right, hypothesis class H, so that is limited. So, that data sample that we have, that is limited, and that is not following the true distribution, you can say, that is not representative of the true distribution. So, they follow distribution, but they cannot mimic the true distribution, right, they cannot represent true distribution. Suppose I give you only the samples that are inside the rectangle here, so this rectangle, and suppose I say that can you mimic this complete distribution? No, you cannot go. If you add little noise, right, you can go little here there, right. So, that is a challenge. If your model is not will not say anything about these samples. If it comes in real time, you have trained your model, you say that your model is good, because you have training, validation and testing data you have chosen from sample S, rectangular sample, right, S. And you might have a certain associated model like this, right, H2, something like that. So, people will generate lot of samples around it, which are very close to this real sample, right. For that your model is not capable of saying anything, it might give random answers, right, or it might give incorrect answers. So, this space is also known as the out space, that is not basically covered by this sample space, training data, the attack space. So, if you know the true distribution, you can develop a model which cannot fed by some adversarial samples, because your model knows all the samples. all type of samples, right. So, you cannot provide adversary to the model. So, because of this reason attacks are possible, and in theory you can say that in practice you cannot get the true distribution, by the way. This is also true. So, that is why uncertainty is there everywhere. Just we are trying to reduce the error with high confidence, that is the only story. We will discuss in the adversarial attacks. So, we will show you that how adversarial samples you can generate, you can attack the models. Very simple model we will show in the demonstration session maybe, and tomorrow session. So, just say here. So, I think now this is clear to everyone. So, BC dimension of neural network architectures, they are generally, you can say, if you have a linear simple perceptron, right, single perceptron, it is of course the same as your logistic regression, or you can say linear regression, it is d plus 1, right, because linear models have indeed dimension is d plus 1. If it is non-linear activation you are using like sigmoid, tan H, ReLU, right, then VC dimension increases, and generally it is quadratic in the number of parameters that you use in the neural network, or it is basically a number of parameters times logarithmic of number of parameters. You can say that if number of parameters are n, then n log n or n square, right. They are quadratic or they are somehow polylogarithmic. So, if number of parameters in your neural network model is huge, then VC dimension is going to be huge. So, if VC dimension is going to be huge, then how will you reduce error? Right. Number of samples you can increase, different type of samples, right. Another one is reduce this VC dimension, try to reduce it, because when you say that VC dimension is high, so true error is going to be huge, training error is small because you have fitted your model H. So, this is the case of overfitting, this is the case of overfitting, right, and training error on H is very small, but because of the other part, second part that you have, that depends on the VC dimension, and VC dimension is huge, number of parameters are very huge in your model. So, VC dimension is huge, so that is why your test error. So, error D is basically distribution error, you can say on real time error that is huge. So, we try to reduce it. So, one is you can increase the number of samples, the other one is to try to reduce the VC dimension. So, choose another model. So, the model that you have chosen, number of layers, number of neurons that you have chosen is huge, right. Try to reduce number of layers, try to reduce number of neurons. Another one is, if you are not able to do it, what you do, because overfitting is somehow you can say over learning, right. So, the samples, training samples are basically learned by the model. So, try to just put some randomization. So, whatever learning is done, try to add some forget mechanism in that. So, that is done, or you just say that okay, controlled learning should be there. So, you can use regularization. So, the parameter you say that okay, the sum of all the parameters absolute sum must be less than certain constant, or you can say it is called regularization, right. So, you can do regularization on the parameters, right, that you have. Another one is, so in deep learning, because you have a huge number of parameters, so using regularization L2 norm or L1 norm on the parameters in the objective function to minimize or in the loss function to minimize is very complex. So, idea is during the learning process what you do, randomly just put some weights 0, some parameter value 0, we call it dropouts. So, if you have worked, if you have done any assignment in deep learning, so you know that if you have a dense layers, so generally we put dropout between the dense layer, because you have a dense connections there. And the idea is it is not that only the fixed, only the some designated neurons are going to get 0 weights. So, in every epoch different set of neurons are going to be get 0 weight or they are not going to be learned. So that is one thing you can do here. So what it will do? So effectively what we are doing? So we are reducing the number of parameters. If you say that many parameter value is 0, so it means that those parameters are not effective for your inference, for your model prediction, right. So if parameters are 0, then there is no need to use them, right. So it means that effectively if you see, the VC dimension is going to be reduced, right. It is because the parameter values, the dimensions are of no use, right. Those dimensions corresponding to those parameters. So it means that this VC dimension we are reducing. So either through regularization. So that's why people call dropout is also one form of regularization in some sense. You can augment the data, increase the number of sample. So these are the two methods we generally use. Try to reduce the model complexity, change the model. So if you say that number of layers you are reducing, you have already changed the model, right. So reduce the model complexity, augment the data. These are the two possibilities that you can use, or lower down your confidence. Just say that delta, earlier your task was to get 99%, with 99.9% confidence you want certain bounds. You say that okay, no, we want, okay, 90% is also acceptable for us. That can reduce the overfitting, right. And other story is the underfitting. Underfitting is there, the first component is high. Error on training data, empirical error, right, on training data is high. Then how will you reduce this quantity? So you try to reduce the second quantity. So suppose your aim is to basically fine tune that model only, right. Then you have to play with the other part. You can just see what you can do. What you can do? You can reduce number of samples, right. So generally it is not advisable because of the distribution theory we discussed. Try to increase the complexity of the hypothesis or VC dimension, you can say. Try to increase the VC dimension, right. So increase the model complexity, right, in some sense. So that training error comes down, right. So this part, this first one, you can say the error on this hypothesis called H comes down when you have a complex model, you have a large number of parameters. So but there is a trade off, right. So if you are trying to reduce one part, the other one will start increasing. If you increase VC dimension, the second part is going to increase. Error on training data is going to reduce. Error S, the first part is trying to basically get minimal value. So there is some compromise at some place. We call it overfitting, underfitting trade-off. What we call it? Overfitting, underfitting trade-off, or many times people call variance. So overfitting is called variance because different time you have different accuracies. So you can say you have a lot of variance in the accuracies, right, in real time. So variance problem. So variance is high. If model is not working well on training data, so it means that bias is high. So it might happen that there is a problem with the data. So we have not touched M in order to reduce this error H basically, but actually you have to look into the data. So your data is not good. Data might suffer from certain bias problem. So that's why the model is not working well. Otherwise, if you increase the VC dimension, so it is expected that your model training accuracy is going to be low, right, down. So you can practice in the tutorial session today. Increase the number of layers, you will see that training error is less, but testing error is going to be high. Right. So now you know that what we have here. So you have a bias, you have a variance, we have a compromise at some place here, you can see, right. So this place, so these many, you can say that model is correct for you, or you can say that this model works well for our data, right? And you can compare other algorithms as well. So this is the theory behind these beliefs of number of samples, number of dimensions. So how many features do we need, how many samples do we need? So is there any guarantee? So we have theoretical guarantee, but these guarantees holds only if your samples are IID and they follow certain distribution. Right. In practice, all the features that you have in the data, so they do not follow certain distribution, any fixed distribution, because of limited number of samples you have. Right. So suppose I say that you have a Gaussian random number generator, right? So normal random number generator, right? Normal random number generator, you just sample 100 points, 100 values, 100 random values, just sample and plot it. You cannot mimic any distribution. You cannot say that whether it is this number, these numbers, random number generated from uniform distribution or Gaussian distribution or some other distribution. But if you now take 1000 samples, you will start seeing that some pattern is there, right? Some pattern is going to be there. Then if you have 10,000 samples, you will see that proper distribution shape is there. And you can just simply put 2 lines of code in Colab, you just write, you will see here. So that tells you that how many samples do we need in order to mimic the distribution. Here you have many features. So if you say that the sample that you have, it is not representative of that distribution, actual or true distribution. True distribution means the samples that you might get in real time. Then your model might face challenges. Right. So we try to make our model robust. So here some models we have and corresponding VC dimensions we have. You might not get in many places, but maybe few of them you can prove, right. So linear classifier in D dimension you have D plus 1, polynomial classifiers maybe degree k, it is order D power k. Decision neural networks, it is order HD, but it is not exactly HD. So H is basically number of basically hidden layers and D is the number of parameters, you can say. Maximum depth, so you can say decision trees, it depends on the depth D because branching factor is finite, by the way. GIAN classifier, K nearest neighbor, you know that GIAN is the simplest classifier where you just say that your data is the model. So if anything comes to you and you have to do inference, you just say that to which class this sample is closest. So that closest, or you can say that similarity metric you can define and then just assign the class. So GIAN has order n to power k classifier, right, because k defines that how many samples basically decides the class, right. So k equal to 1, k equal to 2, k equal to 3, k equal to 4. So this will increase the model VC dimension, right, and n is the number of samples, of course. Then conjunction of Boolean variables, disjunction of Boolean variables, linear threshold function, then support vector machine, right, convex sets, right. Then for neural network we put the little detailed one. So single layer neural network, n small n is the number of neurons, right, you can see here. Multi-layer neural network. So just see that how many, so neurons basically parameters, they define the parameters, right. So you can say, you just see that in the order of the parameters basically that you have layer and parameters, right. Then you have a deep neural networks with many layers, which dimension can go rapidly, and the rough estimate is this one. Exponential, right. So it means that VC dimension plays very critical role in establishing the accuracy. Okay. So this is the theoretical philosophy you should know, right, before applying any model or any classifier. Now I think you understand it well. So, maybe we can stop at this point and we can continue in the next session, right. Actually, we have lot of things to do today. We will share the basically lot of hands on. We made